Good morning. In this class, we are going to have a revision of redox reactions. When you think of redox reaction, the first thing that comes to your mind is oxidation number. So, I expect you to know the simple rules of calculating oxidation numbers. And I am going to focus on certain compounds where the same element exhibits different oxidation states. We'll start with a small definition, however. So, what is exactly oxidation state? I'll explain it with an example of, say, CCl4. We'll just make you feel the oxidation number of carbon in CCl4. What is it exactly? Oxidation number of an element in a compound is the apparent charge, that is, the charge that appears on that atom when all the bonds formed from it are broken according to their electronegativity. Meaning, if you break these bonds one by one, now you take CCl bond. Chlorine is a more electronegative atom than carbon. So if I am breaking this bond, what should I do? Chlorine should be given both the electrons. So you have to break according to the electronegativity. You break it like this. And same way, break every bond. Chlorine is more electronegative. Chlorine is going to take both the electrons. So even here, chlorine is going to take both a shade pair of electrons. So what would be the charge left on carbon now? So carbon is going to be left with, each of them is going to give one positive charge to that. So it is going to have 4 positive charges. And each of the chlorine, we are going to have plus 4 Cl minus. So the oxidation state of carbon in this compound is plus 4, and oxidation state of chlorine in this compound is minus 1. So that is the meaning of oxidation state of an element in a particular compound. And you know the other rules, how to calculate and all. So we will just have a look at certain compounds where the oxidation state is going to be different for different elements. So I'll start with this example, Mn3O4. So by using the rules, we can find out the average oxidation state, that is 3x minus, that is plus 4 into minus 2 equal to 0. If you take that, so x comes out to be plus 8 by 3. Now, in the previous example, we could really visualize the oxidation state of plus 4 for carbon. And here you can't do this because it is an average oxidation state. So, but then what are the oxidation state of individual manganese atoms in this compound? So, to understand that, you need to know that this Mn3O4 is not a true oxide, it is a mixed oxide. So, mixed oxide means the element is in 2 different oxidation state, or there are 2 different compounds in it. So they are MnO2 and MnO. So it is a combination of 1 mole of MnO2 and 2 moles of MnO. So there are 2 moles of MnO and a mole of MnO2 in this particular compound, Mn3O4. So in MnO2, we can calculate the oxidation number, x minus 4 equal to 0. So manganese in plus 2 oxidation state, plus 4 oxidation state, and in MnO, manganese is in plus 2 oxidation state. So the individual oxidation states of manganese atoms in this particular compound Mn3O4 are, 2 of them are in plus 2 oxidation state and 1 is in plus 4 oxidation state. So another similar example is Fe3O4, that is magnetite, Fe3O4. So this magnetite is again a mixed oxide of Fe2O3 and FeO. So Fe2O3, Fe has plus 3 oxidation state, and in FeO it has got plus 2 oxidation state. So it is ferrous oxide and ferric oxide mixture. So they are in the ratio 1:1 in the compound Fe3O4. Not only the oxidation state, you know the exact composition also of this compound. And same way Pb3O4, which we call as red lead. So that is again a mixture of, I think it is similar to Mn3O4. So we have PbO2 in it and 2PbO in it. So it is +4 and +2 oxidation state for Pb. So these are three mixed oxides which are of great importance for our exams. So besides this, there are other compounds which exhibit multiple oxidation state for the same element. You can consider this compound ammonium nitrate. So ammonium nitrate can be visualized as NH4 plus and NO3 minus. So there is NH4 plus and NO3 minus in this compound. So we will take these ions and work out the individual oxidation state. So if we take NH4 plus, so let X be the oxidation state. So X plus 4 equal to +1, the charge on the ion. So X is equal to -3. So in ammonium, nitrogen is in -3 oxidation state. Same way in nitrate, it would be, so let it be Y. So Y minus 6 equal to -1. So Y is equal to +5. So nitrogen is in +5 oxidation state. Let's take a similar example. NH4 NO2. So you can quickly think of the oxidation states of nitrogen in this compound. So this can be again visualized as NH4 plus and NO2 minus. So where we already worked out for NH4 plus, so it is -3, and NO2 minus, it is X minus 4 equal to -1, so N will be +3 in it. And another popular compound, Na2S2O3, sodium thiosulfate or thiosulfuric acid or thiosulfate ion. We call it as hypo. It is pretty much used in redox titrations. So let us see how to work out the oxidation state of this. We can find out the average oxidation state. +2 plus you say 2x minus 6 is equal to 0. So you get x is equal to, you will get +2. That is the average oxidation state. But then what are the individual oxidation states of these two elements in this compound, these two sulfur atoms in this compound? The structure of this compound is we can visualize it as a resonance hybrid of two structures. Many structures we can draw, but then two distinct structures I am going to draw. So we can put S minus, double bond O, and O minus. So let us go by the understanding method of deriving this oxidation state. So now, if you consider this first structure, sulfur is connected to another sulfur, both are equally electronegative. So if I break the bond, I have to break it equally. It is not going to give any charge to this sulfur. So this sulfur is going to have an oxidation state of 0. And from this, it doesn't get any contribution either. But this sulfur is connected to oxygen by a single bond, another oxygen by a single bond, other oxygen by a double bond. When I break this bond, it gets a charge of +1. If I break this particular bond, I'll get another +1. If I break this two bonds, I'll get +2 on this sulfur. So total +1, +1 and +2. So the sulfur is going to be +4. So if I consider this structure to be the final structure, I am going to have a combination of +4 and 0. If I take the second structure, so this oxygen anyway will contribute +2 to this. This oxygen contributes +2 to it, and this oxygen contributes +1 to it, and this oxygen contributes +2 to it, already +5. And this sulfur, already it is negative, that means it has already drawn electrons. You can consider this sulfur to be more electronegative than the other sulfur. So in that case, this sulfur is going to be -2. Already it has got -1, and from this it is going to pull the electron to become S2 minus, and this sulfur is going to be +6 then. So in this case, +6 and -2. So these are the two sets which are accepted for sulfur atoms in thiosulfate ion or thiosulfuric acid. So we can go for any one of these two combination. In a multiple option correct type question in JEE Advanced and all, you can go for both options, and in a single option any one of them would be given, you can easily go for that. Another example I would like to point out to you is C3O2. C3O2, that we call it as carbon suboxide. So it has the structure C, 3 C's are connected together and 2 O's are on either ends. So carbon, of course, oxygen is -2. So oxygen is -2. This is also -2. What about the carbon? So this particular carbon will have +2 oxidation state because of oxygen, +2, and this will be also +2. What about the middle C? So this will be 0. So carbon atom is in 0 oxidation state as well as +2 and +2. I hope you are getting that +0 for middle oxygen, because this C is connected to another C. I don't count this oxidation number of this C to decide anything. It is connected to a carbon of equal electronegativity. So if I break the bond, I'll break the bond equally. So no charge is going to be given to any one of the carbon atoms. So it becomes 0, 0 from either side, 0, 0 from either side. So you are going to get 0 for the middle carbon atom in this compound. Another example, so Br3O8 let us take. Br3O8, the structure of this compound is 3 bromine atoms are connected together, fill rest of the oxygens with double bonds. There is nothing else really you can do. So it is an easy structure to remember. So either ends will have 3 O's and the middle one will have 2 double bond O's. Now what are the oxidation states? The end bromines. So bromine is connected to bromine. This will not give anything to it. The bond is going to break homolytically equally. So we will not have any charge accumulated on this bromine due to breakage of bromine-bromine bond. But if I look at oxygen bonds, okay, so there are 3 O's which are connected by total 6 bonds to this. So when I break that, as oxygen is more electronegative than bromine, it should give a charge of +6 to this bromine. Same way, the other end bromine, that will also have an oxidation state of +6. What about the middle? It is connected to 2 bromines on either side. Ignore, they do not contribute anything. So it is only due to these 2 oxygens that is going to get +4 oxidation state. The other interesting compound, which is pretty popular and you would be knowing it, CrO5. CrO5. So we call it as, it has got a butterfly structure. So the structure is Cr and a double bond O. Now what are these oxygens, these special bonds? So this OO, these 2 O's and these 2 O's are connected through a peroxy bond. These bonds are peroxy bonds. So peroxy bond, it is given an oxidation, each peroxy oxygen is -1. And look at chromium. Chromium is connected to 6 oxygen atoms. I'm sorry, 5 oxygen atoms, but through 6 bonds. There are 6 bonds with more electronegative atoms. So the oxidation state on chromium is going to be +6. That is the most popular oxidation state of chromium anyway. But then the oxygens are famous. Oxygen is in -2 as well as -1 oxidation states in this compound. That means there are 2 kinds of oxygens in this compound. I'll just finish this oxidation state, the one last compound, that is, we'll take H2SO5. We call it as peroxo monosulfuric acid, H2SO5. So what is the structure of this one? We can't decide the oxidation state again by the normal calculations. So S sulfur, it is like sulfuric acid. You can start like sulfuric acid, double bond O and a OH. Instead of one OH, there will be a OOH bond. As the name suggests, peroxo monosulfuric acid, it has got a peroxo bond. So peroxo bond, sulfur, anyway, peroxide has to be -1 and this will be -1. And this oxygen is -2, this will be definitely -2, this will also be -2, and the sulfur is, so it is connected to 4 oxygen atoms through 6 bonds. So the oxidation state of it is going to be +6. Again, it is not famous for sulfur. Sulfur will be +6 only, but it has got 2 different kinds of oxygens. So 3 oxygens are -2 oxidation state. They are in -2 oxidation state, while 2 of them are in -1 oxidation state. Then you will see different types of redox reactions. We can classify redox reactions just like we do in case of normal reactions like combination, displacement, double displacement, decomposition, etc. I would like to highlight on few important types of redox reactions. Let us see. One is disproportionation. What is a disproportionation? So in disproportionation reaction, a compound it degrades, okay, it gets converted into 2 different compounds in which the element goes in different oxidation states. That is, you take Cu plus, you have Cu plus undergoes a disproportionation, giving Cu2 plus Cu. That is, Cu plus changes to Cu2 plus and Cu. So Cu plus has become Cu2 plus. That is, Cu plus gets oxidized to Cu2 plus by losing an electron. And Cu plus gains an electron to give you Cu. So the same element from one oxidation state changes to 2 different oxidation states. That is called a disproportionation reaction. So you will take here, if you want to balance it, you will put 2 here, the reaction is balanced. So 2 Cu plus changes to Cu2 plus and Cu. Such reactions are called disproportionation reactions. Other popular example is Cl2 changing to Cl minus and ClO3 minus, where same molecule, chlorine molecule, changes to, from its 0 oxidation state, it changes to -1, and here chlorine you can calculate it to be +5. So here it changed from +1 to +2 and +1 to 0. In this particular case, in chlorine case, so chlorine from 0 it went to -1 as well as +5. So same atom is undergoing reduction. This is reduction and it is getting oxidized here. Same atom undergoing oxidation and reduction is disproportionation reaction. The another type we want to concentrate is comproportionation. What is comproportionation? Look, think of the reverse. That is, Cl minus plus ClO3 minus getting together to form Cl2 under suitable conditions. Cl minus plus ClO3, Cl minus and ClO3 minus getting together to form Cl2 is comproportionation. What is that? So chlorine is in -1 oxidation state. Here chlorine is in +5 oxidation state. So the same element in two different compounds in two different oxidation states get together to form a single compound in a different oxidation state, that is 0. So -1 becomes 0, +5 becomes 0 ultimately. That is called a disproportionation reaction. Then another type, let's see, intramolecular redox reaction. What is this intramolecular redox reaction? So here the electron transfer happens within a molecule, just within a molecule. So NH4NO3 let us take and heat it strongly. I hope you all know this reaction. Ammonium nitrate, it is an explosive compound. It on heating gives you N2O plus H2O. Relatively low temperature. At high temperatures it gives nitrogen basically. N2O and H2O. Now see, I already talked about the oxidation states of nitrogen and ammonium nitrate. So ammonium nitrogen is in -3 state and nitrogen is in +5 oxidation state, and they are getting together to form a compound in which nitrogen is in +1 oxidation state, that is 2x minus 2 is 0, so it is +1 oxidation state. So -3 and +5 are getting together to form, that is, there is a 4 electron gain and there is a loss of 4 electrons. That means it is gaining 4 electrons and here there is a loss of 4 electrons. So internally the electrons are getting balanced. So that is called an intramolecular redox reaction. Another example is NH4NO2. Heat. So you'll get N2 plus H2O. The reaction is balanced if I put 2 H2O. Here nitrogen is in -3 and +3 oxidation states. So nitrogen is in -3 and +3 oxidation state and it is ending at 0. So -3 to 0. So it is gaining 3 electrons. And -3 to +3 to 0, it is gaining 3 electrons. -3 to 0, it is losing 3 electrons. So the electron lost by one nitrogen is gained by the other nitrogen. So the electrons are internally balanced. So we call it as intramolecular redox reaction. Now let's see how to calculate valency factor for a substance undergoing oxidation or reduction. Valency factor, or you would have learned it as N factor, any of them is okay. Valency factor or N factor for an oxidant or reductant. So we call an oxidizing agent as oxidant or reducing agent as reductant. Let us see how to calculate valency factor for an oxidant or reductant. So the valency factor for an oxidant or reductant is the number of moles of electrons transferred per mole of oxidant or reductant. Single rule, number of moles of electron transferred per mole of oxidant or reductant is the valency factor for an oxidant or a reductant. We'll take some simple examples and explain. Let's take this. Cl minus changes to say ClO3 minus. How to find out the valency factor for this? So chlorine is in -1 oxidation state, and on the right hand side chlorine is in, you can calculate it, x minus 6 equal to -1, so it will be +5. So how many electrons are transferred in this process? So there is one chlorine atom on this side. So what I do is -1 into 1. Why 1? Because only one chlorine is here. And I am interested in, okay, it is going to +5. I am interested in only one chlorine atom. So into 1. So the change is -1 to +5. That is, the N factor for this substance is 6. So when chloride changes to ClO3 minus, the valency factor for it is 6. Let's take another substance, Cl2 changing to say Cl minus. What is the valency factor? Oxidation state of chlorine on the left hand side is 0 and right hand side is -1. Now is the valency factor 1? No. Definition is number of moles of electrons transferred per mole of the substance getting oxidized or reduced. So if you take that way, the 0 into, I have to take 2 atoms because there are 2 chlorines. And on the right side, -1 into, I have to take 2 because reactant has 2 chlorines. I have to take that chlorine atoms on the right also. So net is 0 to -2. So the number of electrons, the valency factor is 2 for it. Let's take another one. Cr2 O72 minus changing to Cr3 plus. Quickly you can work it out. It is, chromium is in +6 state, so +6 into 2, and here it is +3, so that is the oxidation state, leave it. So I have to take +6 into 2 atoms I have to take, and it is changing to, of course, +3 it is changing to, how many atoms should I consider? Again, I should consider 2 atoms because my reactant has 2. So it is net changes, it is +12 is changing to +6. So the N factor for this is 6. Next, let us take thiosulfate S2O32 minus changing to tetrathionate, that is S4O6 2 minus. So to find out this N factor, you need not go for individual oxidation numbers, you just take the average oxidation numbers. So that is only for a specific question. We need to break it into write the structure, draw the structure and work out the oxidation numbers. Let the compound be any complex. You need not worry about it. You find out the average oxidation number to find out N factor. So that way, let us take the average oxidation number on the left side. So 2x minus 6 equal to -2. So x is equal to +2. So the oxidation state of sulfur in thiosulfate is +2, that is average oxidation state. On the right side, 4x minus 12 equal to -2. So 4x is equal to 10. So x is going to be 10 by 4, that is 5 by 2. So it is plus 5 by 2. So now I have to calculate the valency factor. So it is +2 into, in 1 mole, how many moles of sulfur atoms are there? There are 2 into 2. 2, it changes to plus 5 by 2 into, I need to take 2. There are 4, but I am not bothered about it. Don't balance it by putting a 2 here and to do it. Okay, that is wrong. So you just do by exactly what I am saying. So plus 2 into 2 because 2 sulfur atoms, and plus 5 by 2 into 2. It's not this 4, it is the 2 of the reactant, because we are interested in the fate of only 2 sulfur atoms which are there in the reactant. So it is plus 5 by 2. So overall it is plus 4 changing to plus 5 net. So the valency factor for this compound is, that is thiosulfate, is 1. Let's consider a compound undergoing disproportionation. So I'll take this Cu plus changing to Cu2 plus and Cu. So consider this reaction. So you'll find out the valency factor for copper plus. So how you do? take copper plus, change it to copper 2 plus. So to balance the electrons, you'll be adding, balance the charges, you'll be adding 1 electron here. Like this, you write the reduction half also. So this is oxidation, reduction half also. Reduction Cu plus plus an electron giving Cu. So if you add both of them, you will get the net equation. What is that? 2Cu plus gives Cu2 plus plus Cu. I'm making you feel it. Just see. In oxidation, 1 electron is lost, liberated. And reduction, 1 electron is gained. That means how many electrons are transferred? 1 electron lost and 1 electron gained. That means an electron is, the electron which is lost here, that is being gained here. So 1 electron is transferred. And to transfer 1 electron, 1 mole of electron, how many moles of copper 2 plus are required? 2 of them are required. So that means what is the number? 2 moles of copper together transfer 1 mole of electron. And we require number of moles of electron transferred per mole of copper. That means the valency factor for copper plus in this case is there is 1 electron transferred between 2 moles of copper plus. So the valency factor is 1 by 2. We have not seen so far fractional valency factors. So valency factor, n factor can be even fractions, but it won't be negative, you know. So it can have a fractional value, it can have any other integral value as well. So you'll see one more example for disproportionation. Say let's take the same one, Cl2 giving Cl minus plus ClO3 minus. I will work out the same way, Cl2 changing to Cl minus. So 2 chlorines, you put 2 here. So it is like we need to add 2 electrons so that the reaction is balanced. And same thing you do, Cl2 changing to ClO3 minus. Don't balance anything else. There are 2 chlorines, you take 2 chlorines here. Okay, 2 chlorines. So it is 0 and it is becoming plus 5. So 0 into 2, 2 plus 5 into 2. That means 10 electrons. So it has to lose 10 electrons. So I'll just remove this. So you have to know how to get that 10. So Cl isn't 0, it is becoming plus 5. There are 2 chlorines. So total 2Cl becoming 2Cl plus 5. So the total number of electrons lost will be 10. So now you balance this electrons. Balance the electrons in oxidation half and reduction half. Multiply it by 5. So 10 electrons, 10 electrons. So we will get 5 plus 1, 5 plus 1, 6 chlorines, giving 5 into 2, 10 chlorides plus 2 ClO3 minus ions. So there are 6 moles of chlorine involved. And how many moles of electrons are involved? There are 10 moles of electrons involved among 6 moles of chlorine. So n factor for this case is 10 moles of electrons or number of moles of electron transferred per mole of the substance. That is 10 moles of electrons are transferred among 6 moles of chlorines. That is equal to 5 by 3. So the valency factor for chlorine undergoing disproportionation as Cl minus and ClO3 minus is 5 by 3. Now let's take a system where 2 different atoms in the same compound undergo oxidation. I'll take AS2S3, arsenic sulfide changing to ASO4 3 minus plus SO4 2 minus. So in this particular case, arsenic is in plus 3 state, sulfide you can take minus 2, sulfur is in minus 2 state and arsenic is in plus 3 state. And you can work out for this, x minus 8 equal to minus 3, so it will be plus 5 and sulfur is in plus 6 oxidation state. Now we will work them out individually. So sulfur is in arsenic is in plus 3 state. there are two arsenic atoms. So plus 3 into 2 is changing to plus 5 into 2. So here the beauty of this is arsenic is going to plus 3 to plus 5, it is getting oxidized. Arsenic is getting oxidized. Sulfur is also from minus 2, it is becoming plus 6. Both are getting oxidized. So plus 3 into 2 to plus 5 into 2 is for arsenic. So the number of electron transfer that way is, it is plus 6 changing to plus 10. So the number of electrons transferred is, there is a loss of 4 electrons here. Let's see for the other one. That is sulfur. Sulfur is in minus 2 oxidation state. Minus 2 into, there are 3 sulfur atoms, which is changing to plus 6 on the right side. And as there are 3 sulfur here, we need to consider 3 sulfur on the right side as well. So it is minus 6 changing to plus 18. So minus 6 to 18. Minus 6 to 6 and 18. So total the number of electron transferred is, I think you know, it is minus 24 electrons. So the total number of electrons that way is, so there is a loss. Loss of electrons is oxidation. So both are losing electrons and there is an overall loss of 28 electrons. So the valency factor for this substance is 24 plus 4, that is 28. You add both of them up. So you'll get valency factor of 28 for arsenous sulfide if it undergoes oxidation to AsO4 3 minus plus SO4 3 minus. Let's consider another example. A non-stoichiometric compound Fe.90 changing to Fe2O3. So how to work out the valency factor? I'm not getting into the detail of this particular compound. We will do by average oxidation number. Let us see. So what is the average oxidation number of Fe in this? 0.9x minus 2 equal to 0. So x is equal to 2 by, so you say 20 by 9. So that is the average oxidation state of Fe in this compound. And on the right hand side it is Fe2O3. So obviously it is plus 3. Now how to get the valency factor or N factor? So the average oxidation state is 20 by 9 into how many Fe's you have? You have got 0.9 Fe. So into 0.9 changing to plus 3 is the oxidation state into 0.9. Why 0.9? Because the compound of your interest is Fe.90. That means 1 mole of the compound contains only 0.9 moles of Fe. You consider that on either side. So what are you going to get? So 0.9. So it is going to be 2 plus 2 on the left side. So it is plus, right? Plus 2 to plus 2.7. So the valency factor for this particular compound is 0.7. 0.2 to 2 to plus 2 to plus 2.7, it is 0.7. Next we will do balancing of some redox reactions. So let's take an example. MnO4 minus reacting with Fe2 plus to give Fe3 plus plus Mn2 plus under acidic conditions. So whenever they give this balancing, so you'll be provided either acidic or basic conditions. Either it will be part of the reaction or it will be written acidic or basic conditions. And it has become a popular question. They will ask the stoichiometric coefficient of any one of the oxidant or reductant or a product, any of them. Okay, so you need to be thorough with it. And I'm just going to do it in a step, okay, single step, because the ion electron method would be useful in electrochemistry. There you will see. Otherwise, it is independent of the method. Okay, so you need not bother about which method by which you are solving. So you have to get it correct. Okay, so probably the method will be short. Just listen carefully. So I'll rewrite the reaction. Say MnO4. Okay, we'll calculate in that only. From the given reaction, in the given reaction itself, we'll find the oxidation states of these different elements. So manganese, it is in +7 state. You can work it out, and Fe is anyway +2, and here Fe is in +2, and manganese in +2 state. So you find out the oxidation states. Now you see, one of the substances getting oxidized. So you know, +2 to it is +3, +2 to +3. It is oxidation. It is getting oxidized, and then this one manganese is from +7. It is getting reduced to +2. So here there is a gain of 5 electrons, and here there is a loss of 1 electron. 1 electron is lost. So you find this out first. So after that, you just rewrite the equation once. MnO4 minus plus Fe2 plus giving Fe3 plus Mn2 plus. So what you do is exchange these numbers as the coefficients of the oxidant and reductant. I'll just label them. Yeah, just see. So this is 5 electrons, and yeah, take this. This is say 1. Just to differentiate between the electrons, where exactly they are going, we will track. So just see, 5 and 1 electrons are there, and it is like it's a redox reaction. In a redox reaction, the electron lost by one substance should be gained by the other. The substance getting reduced should gain electrons from the substance getting oxidized. So the electrons, again the sign went wrong here, so it is -1 electron. Yeah, -1 electron and plus 5 electron. So you MnO4 minus, the coefficient is going to be that 1. That is going to be its coefficient. And the coefficient of Fe2 plus is going to be 5. That may be exchanged that. Now you see, it's interesting. So 5 is the coefficient of Fe. 5 Fe2 plus are becoming 5 Fe3 plus. So 1 Fe2 plus became Fe3 plus will lose 1 electron. So 5 means 5 electrons are lost. And how many electrons are gained by manganese? 1 manganese is going to become, this also is going to have a coefficient of only 1, which we need not write, but just for our reference we are putting it. So 5 electrons it is going to gain. That is coming from Fe2 plus getting oxidized to Fe3 plus. These coefficients should not be changed now. Leave them. Now we will try balancing it fully. So we got the coefficient of oxidant and reductant and their respective products. Next what you do is, independent of whether it is acidic medium or basic medium, you first do it in acidic medium, then we can convert in one step into basic medium. So here it is anyway given in acidic medium. How to, what to balance now? Other atoms are all balanced. Oxygen you don't bother about, but you balance the charges by adding H plus on the required side. So if you balance the charges, there are 5, 2 plus, 5 into 2, 10 plus here. So there are total plus 10, and here it is -1. So the net charge on the left side is plus 9. On the right side you look at 15 plus 15 plus 2. It is 17 plus 17. We need to balance it. So we need to add 8 positive charges on the left side. So what you do is you add 8 H plus ions here. 8 H plus. Now you just balance hydrogen. So you just put 4H2O on the right side. I'll just write it down. The 17 is for reference. Okay, let it be here. So plus you'll get 5. So 8 hydrogens. So 8 hydrogen means you need to put 4H2O. Now you count oxygens, it is balanced. The equation is balanced. So I took the time to explain, but then you can do it in very short duration of time. Just find out the electron transfer by oxidant and reductant carefully. Just that is that valency factor you find out, and exchange them for the coefficient of the other substances. So understand it well, because 5 into 2 10, 5 into 3 15. So there is a transfer of 5 electrons. That electrons are going to MnO4 minus to reduce MnO4 minus. So here the oxidizing agent is MnO4 minus, reducing agent is Fe2 plus. Okay, let's consider another reaction in acidic medium again. Dichromate reacting with Sn2 plus in acidic medium to give Sn4 plus and Cr3 plus. Let's try quickly applying that method. Now the oxidation state, it is plus 6 for chromium. You can find it out. Plus 6 into 2 I will take. And this is anyway. So plus 2, plus 4, and this is plus 3. So plus 2, there is one tin, and that is changing to plus 4. And the number of electrons transferred here is plus 2 to plus 4. So it is losing 2 electrons. So minus 2 electrons here. And consider the next one. It is plus 6 into 2, the valency factor I mean to say. So it is plus 3. I'll remove this 2. Let it be. Okay, so plus 6 is the oxidation state, plus 3 is the oxidation state for chromium 3 plus, and plus 6 into 2, it is becoming plus 3 into 2. So the number of electron transferred from here to here, it is 6 electrons. Okay, so we'll choose a different color. Okay, so it is transferring, it is gaining 6 electrons. So as I told you, now you have to exchange the coefficient. Before that, you see the 6 and 2 are like, they are not in the simplest ratio. So what you can do is, you can make it in the simplest ratio. You make this into 3 electrons, and the other, this one, into 1 electron. So this you make into 1 electron. So the coefficient are going to be, the coefficient of this 1 comes here. So this is going to be 1, and this is going to be 3. So you are going to have 3 tin here. So 3 is going to be the coefficient of this. Once these coefficients are decided, you can fill the coefficients on the right hand side. So it is going to be 3 again. So this is, the other is going to be, so this coefficient is going to be, it's not 1, because 1 dichromate contains 2 chromium. So you put 2 here. Now balance the charges by adding H plus. So the charge on the left side, so 3 into 2, you got 6 plus 6 and minus 2. Minus 2 plus 6. The charge is going to be plus 4 on the left side, and the right side we got 3 10, like plus 12 plus 12 plus 6. You got 18. So that is plus 18. So what should I do? I will add 14H plus on the left side, so that the equation is balanced by charges. Now 14H plus, so I'll add 7H2O to balance it fully. I'll have 7H2O. Your equation is perfectly balanced. So it is Cr2, the final equation is Cr2O7 2 minus plus 3Sn2 plus 14H plus, giving 3Sn2 plus 2Cr3 plus 7H2O. That is the balance equation. And commonly what we get is they will ask the coefficient of one of the element, or in an objective question they can put even all the coefficients and ask, okay, the coefficients of this, I don't know, a b c d e f g, the values of a b c d e f g are, okay, that also can be answered. So no, a shorter method rather than doing by ion electron method for solving an objective question. Let's consider this particular reaction, As2S3 plus NO3 minus giving ASO43 minus plus NO. I just worked out the valency factor in this class itself for As2S3. I think we got it to be 28. That means As2S3, I think I missed a product. It should give plus SO42 minus plus NO. That is the reaction. So now we already worked out for this As2S3 becoming these two products. The valency factor we found to be 28. You can refer that back, 28 electrons. Okay, so is what it is. They are getting oxidized, so they are losing 28 electrons. Now let us look at this nitrate. What is happening to nitrate? So the oxidation state of nitrogen in nitrate is, it is plus 5, and here it is plus 2. So that means plus 5. From plus 5 it is changing to plus 2. So it is plus 5 into, oh sorry, there is no into because only one nitrogen is there. So the number of electron transferred here is, so the number of electron transferred on going from this to NO is 3. So there is a gain of 3 electrons. Here the loss of 28 electrons. No, they are not, they are already in simple ratio only. You can exchange the numbers. So the coefficient of As2S3 is going to be 3, and this is going to be 28. 28. Now I'll balance all the atoms other than charges. Okay, 3 into 2, 6 arsenic, so it should be 6, and 3 into 3, 9 sulfur, so it should be 9 sulfate, and 28 Ns, and it must also be 28 NO. Next what? Balance the charges. So here the charge is minus 28. On the right hand side the charge is 6 into 3 minus 18, minus 9 into 2 18, and there is no charge on that. H plus we leave. Okay, so the charge here is minus 36. Now we need to add H plus on suitable side to equate the charges. So where should we add? Minus 28, so we can equate them by adding 8 is a difference, so you can add 8 H plus on the right hand side. 8 H plus I can add on the right. So minus 36 plus 8, that will become minus 28. Now 8 hydrogens are there. Here there are no other hydrogens, so I will add simply 4 H2O. In case you have a doubt, you check the oxygens. What are those? 28 into 3 oxygens plus 4. Count the oxygens. I think it must get balanced. It must be balanced. Okay, it will be definitely balanced. There is no need to suspect. So we have got 8 H plus we put for balancing the charges on either side, and correspondingly add 4 moles of water. So that would take care of the whole reaction. Now we'll balance this particular reaction in basic medium. As I told already, you just balance in acidic medium, and finally we do a transformation to convert this into basic medium. There is no need to know two different methods. So if you go by that, so it is plus 7, it is in minus 1 state, it is in plus 5 state, it is in plus 4 state. So the number of electron transferred here is, so it is minus 1 to plus 5, so it is 6 electrons. And if you take this plus 7 to plus 4, plus 7 to plus 4, it is transferring, so 3 electrons, 6 electrons and 3 electrons are transferred. Now you exchange this and they are not in the simple ratio, so you make them in simple ratio. So it is 2 and this is going to become 1. So the coefficient of I is going to be 1 and the coefficient of Mn is going to be 2. So if it is 2, here it is going to be 2 and iodine again. So this is going to be 1. Now balance the charges. As I told you, just balance the charges. To balance the charges, you are going to use H plus. You just use H plus. Now what are the charges? On the left side, minus 2, it is minus 1. That is equal to minus 3. And right side, minus 1. It is just minus 1. So we have to equate the charges. So what should I do? I will add 2H plus on the left side plus 2H plus. Now hydrogen is not balanced. I will add H2O, 1 mole of H2O on the right side. Forget about this now. 1 H2O. Is the equation balanced? Count the oxygens once. 2 into 4, 8 O's. 3 plus 4, 7 plus 1, 8. Charges are they balanced? Minus 1, net charge is minus 1. It's perfectly balanced in acidic medium. But the question was in basic medium. So what should I do? Now what you do is take the reaction again. So 2MnO4 minus plus I minus plus 2H plus giving IO3 minus plus 2MnO2 plus H2O. This is what you have. Now what you do is add, I'll just take some more space, wait. Yeah, what you can do is add, you don't want to have this H plus. So how do you remove that H plus? You add 2 OH minus on the left side. If you add to the left, you have to add to the right as well. So meaning I am going to put 2 extra OH minus here. So plus 2 OH minus on the left side and I will add 2 OH minus on the right side as well. Add the equations and cancel if there is anything that is common. Now 2H plus plus 2 OH minus will give you 2 moles of water. There is already 2 moles of water. I'll cancel out that water on the left side and right side. Cancel out. So and combine the rest and write the equation. So what is the equation? So it's going to be 2MnO4 minus plus I minus giving IO3 minus plus 2MnO2 plus 2OH minus. The equation is perfectly balanced. Count the oxygens once. 2 plus 4, 6 plus 3, 9. Yeah, we made a small copying error. Here there is only one H2O. I wrote here 2 H2O. That should be cancelled. Okay, it is just one H2O. So that means 2H plus plus 2 OH minus gives 2 water. And here there is 1 water. So obviously from this 1 will cancel out. So 1 water is out. And this is out. Completely out. So the equation becomes 2MnO4 minus plus I minus plus a mole of H2O. Giving IO3 minus plus 2MnO2 plus OH minus. So the equation is perfectly balanced. 2 into 4, 8 oxygens plus 1, 9. Total 9 oxygens and 3 plus 4, 7 plus 2, 9 oxygens. So the equation is perfectly balanced. I think you can always check once when you write the final equations. I could make out my error by writing the final equation, just counting the number of oxygens. That is essential. That will be a check. If you would have done any careless mistakes, you would be able to correct. Thank you.